So before we continue on to other privacy-preserving deep techniques, I would like to first talk about garbage collection and a few of the common errors that people seem to run into when using PySift to control tensors on remote machines. So first, let's talk a little bit about garbage collection and the life cycle of remote objects. So if we were to clear all the objects in Bob, just so it's easy to tell when something gets deleted, so we'll see Bob underscore objects is now empty, right? This is the collection of all the objects on Bob. And if we were then to create a tensor and send it to Bob, and then if we were to delete our pointer to this tensor, so x, as you know, is our pointer. I'll show this first, just so you can see. Bob's object is there. And if they were to delete this, what should happen? Well, PySift always assumes that when you created the tensor and sent it to someone, you should continue to control the life cycle of that tensor. Which means if you delete your pointer to the tensor that you created and sent, the tensor that you're pointing to should also get deleted. Now, this is controlled by a very specific attribute on each pointer. So if I was to create another pointer, x.child.garbageCollectData. By default, this is set to true when you call .send. And this means when, sort of me, the pointer, when I, the pointer, get garbage collected, should I send a message to Bob saying, hey, go delete that tensor? And by default, this is set to true. So if we set this to false, then this would actually turn garbage collection off for this pointer, and it would no longer send a message to Bob saying that it should delete tensors when they get removed. There's an interesting gotcha when working in Jupyter notebooks. So normally, so Bob has this object right now, right? And if I said, x equals ASDF, and this got garbage collected, Bob would lose it, right? So now Bob is empty. However, Jupyter notebooks have this thing where they store every command you've ever executed. And so occasionally, if you do a few commands, they'll get cached in such a way where garbage collection will no longer collect those objects. And so you might end up with just things, just by virtue of the fact you're working in a Jupyter notebook, it can keep a couple extra objects around. So let me show you what I mean specifically. So if we create another one of these, and then we go x, and we just call the double under Reaper here, then if I go x equals this, Bob has this, x equals ASDF, there's still a reference to it. The pointer never actually got garbage collected. Even if we go delete x, right, it still lives on, right? But this is not because of some issue with PySift, or it's just an issue with, sort of a known gotcha when you use Jupyter notebooks. There are some things that actually end up having another reference to the object that you have in your notebook, and thus, since this pointer doesn't get deleted, right, since this pointer doesn't get garbage collected, it never sends an execution or a command to the remote worker telling it to delete the thing that it's pointing to, right? So this happens occasionally. So now I'm going to go ahead and go erase these again. So Bob equals Bob dot clear objects, Bob dot objects. So clear this one more time. And then I just want to show you that this garbage collection works for like for loops and stuff too. So if I were to do for I in range 1000 x equals x dot send, or sorry, th dot tensor. So if I were to send this tensor to Bob 1,000 times, Bob dot object should still only have 1. And the reason for that is every time this for loop went through again, it reassigned x and deleted the tensor that was returned from here, which caused it to be garbage collected from the remote machine. Now, why is this important? The reason this is important is that it means that when you're doing, say, federated learning, or you're doing the exercise, the project that we did previously, where we had we were learning a simple linear model, when we iterate through this for loop, and we're generating, a new prediction tensor, a new loss tensor, and like all the intermediate tensors that go into executing each of these parts, if we end up deleting our reference to that execution, then the remote machine will also delete it. And this is like a really good default piece of behavior to have, because otherwise, when we ran this for loop, we would end up generating and persisting, thousands of tensors, even when we're doing just simple forward and back propagation. So it's just a good thing to know about this particular sort of garbage collection feature, so that you know that, when objects are created or seem to disappear from remote workers, that they're actually attached to the pointers that are pointing to them. I know it might seem like a little bit of an advanced thing, but it's just something you sort of need to know about as far as what are the core assumptions of how this API is built before jumping into too deep into federated learning and into your own sort of custom projects. Now, there's a couple other sort of convenience errors that I wanted to also mention while we're here. So let's see, does Bob still have, yeah, Bob still has this. So x equals th tensor 5. So let's create x and y. But I'm not going to send y to Bob. I'm going to try to call a command on both. So again, x is a pointer to Bob. Y is a data set tensor that I have here. Right? So if I do this, it returns an error. Pure torch tensor found error, which means that one of these was a regular torch tensor, one of these was a pointer to one. If we scroll down to the bottom, it'll say you tried to call a method involving two tensors where one tensor is actually located on another machine. It's a pointer tensor. Call .get on the pointer tensor, .send to Bob on the other tensor. So this gets populated automatically. Here are the two tensors that we tried to work with, and this is really just to try to make it obvious when you accidentally do this. Another common error that people will do, so we can scroll down here, is send Alice on two different machines, and we'll get a very similar error. So you tried to call add involving two tensors which are not on the same machine. One tensor is on Bob, while the other tensor is on Alice. Use a combination of move, get, or send to co-locate them to the same machine. So again, if you see these, just follow the instructions, and hopefully you'll be led to the right sort of series of operations that you're interested in performing in the first place. All right, the next session we're going to jump a little bit deeper into sort of privacy-preserving deep learning techniques using these core primitives. See you then.